Okay, we've got Sarath here. He's got all these like chairs. He's got so many places to sit. So now he's going to tell us about critical gradients.
Thank you for hosting me on short notice, Mark. So I was here for AAA, and well, as I will talk about today, like in my group, like we are getting more interested in doing optimization, and I thought this would be the apt place to talk about some of these projects and also like hopefully interest you in some of these problems and get more feedback on seeing like how we can see these from the optimization perspective. Okay, so I will be talking about, well, the general theme of the talk is memory-augmented optimizers. Like, so I will explain what I mean by memory augmentation. It's like, and so we'll start with like basic, like more general class of optimizers for deep learning. Then towards the end, I also want to talk about how to design like specific optimizers for the problem of lifelong learning. So before we begin, like a very quick overview of like higher level research that we do in my lab. Like, so like we broadly work in deep learning, reinforcement learning, and NLP. And my long-term vision is to develop interactive learning algorithms that can continually learn from experiences. Okay, so I'd like to stress two parts here. Like, so like one, I'm more interested in interactive algorithms. Like, so this kind of includes things like reinforcement learning, NLP, like where we have things like chat systems, etc. Right? Like, so systems that can interact with you and learn through these interactions. Okay? It could be natural language feedback like NLP, or it could just be simple reward feedback like reinforcement learning, right? And I also care about systems that can continually learn and improve themselves, like sometimes even after deployment, which is kind of essential if you care about things like self-driving cars, because you can't wait for the next software update to improve your car, right? Like, so how do we design systems that can continually learn from experiences? Like, so which is where the idea of lifelong learning comes in. And if you are interested in lifelong learning, like, so we also have this conference on lifelong learning, which like we have been running for 3 years. Like, so the third edition is going to be in Italy. The submission deadlines are already over, but we do have a journal track where you could present your TMLR papers or any other journal papers. And papers from TMLR will get a special certification from TMLR for being presented at COLAS. Okay, so these are all the topics like which we are interested in. Like the broad idea here is really learning in non-stationary settings, like or non-IAD settings, let's say, which includes things like continuing learning, meta learning, active learning, online learning, etc. Okay, so that's just a quick advertisement for the conference. Like, now let me get back to the actual talk. Like, well, this is kind of a redundant slide nowadays. Like, so I don't want to spend too much time in convincing you that there has been this huge progress in deep learning. Like, so, and I think it actually includes some of the progress from the last couple of days, like things like Gemma, right? So we started with ImageNet, and we have come a long way in the last 10 years, right? Like, so things work really well, like compared to what used to be like 20 years back, right? Like, so what's the reason for this? So like there are some secret sauces. Like, however, one thing I would like to highlight is the whole idea of training a neural network to solve a task, right? Like, so this is not like, this has not been like completely changed, right? Like, so we still use similar architectures and similar training regimes from 80s, 90s, right? Of course, there are a bunch of modifications which helped us to train them in a more efficient way, and sometimes even help us to train deeper networks, right? Like, so the main frequent recipes here are like, well, first data. Like, so we got a lot of data in the last decade, like, so which kind of helped us to scale things, right? Like, and also compute, GPUs, TPUs. Like, so now I think Grok has their new LPUs, like which are even more faster. Well, at least they claim that they're faster than TPUs, right? And also a bunch of architectural changes, right? So we discovered dropout, Velu. We still argue why batch-norm works, but we know batch-norm works, right? Like, so, and residual connections, attention is probably one of the major recipe that we discovered, like which helped us to scale things like transformers. Also optimizers. Okay, so like one of the reasons why we were able to train deeper networks is because we kind of figure out how to do adaptive gradient methods, like, which helped us to solve some of the vanishing and exploding gradient problems like that we face with recurrent neural networks or even just deeper neural networks. So in this talk, I would like to focus more on optimizers. Well, so this is like a one-slide introduction to optimizers, which I'm pretty sure I don't need to do for you, but still, like I will do it to set the notations. So first we have stochastic gradient descent, like the simplest possible optimizer, like where theta is theta minus some learning rate times the gradient, right? Then we have a few families of optimizers that we often use. Like one of them is momentum, like where you use a separate momentum vector, mt, and you integrate the gradients over time, which helps you in accelerating the gradient descent. And we have adaptive learning rate methods like RMS prop, like where the basic idea is you want to adapt the learning rate. Like now, what do you use to adapt learning rate? Gives you different optimizers. In RMS prop, it's root mean square of the gradient, right? Like and if the gradient size, if you see a lot of small gradients, then the step size gets larger. If you see a lot of large gradients, the step size gets smaller. And of course, you can combine these two methods, like, which is where you get ADAM, which is basically a combination of adaptive learning rate and momentum, right? Of course, there are hundreds of variants that people publish every day, but this kind of gives an idea of like what are the existing families of optimizers. Now, I want to look at all these optimizers from the memory perspective, okay? So which is the theme for today's talk. Like so, if you think about the memory requirements of these optimizers, right? Like so we have the simplest possible optimizer, SGD, which is memoryless. So if you think about how, like, imagine there's an internal stateful optimizer which is used to like optimize better, right? So in that sense, SGD is a stateless optimizer. Like so, at every time step you do a gradient update, then the optimizer forgets what happened. It is doing another gradient update, right? Now, methods like momentum and like RMS props, they do have some memory, right? So in this case, the memory vector is either empty in your momentum or the root mean square of the gradients that you store in the vector that you use for the denominator, right? And so now this is some memory which kind of tries to remember what happened in the past and use that to either accelerate better or change your learning rate.
Theta T is in memory too.
Sorry?
Theta T is in memory too.
Oh yeah. Well, yes, like, but I think
there are algorithms that don't have a theta T.
Yeah. So we could consider theta as a memory too. But I think from the optimizer's side, like, so I kind of separate the model and the optimizer right now. So in that sense, like, theta is in the model. Okay, so this is nice. Now, well, I come from recurrent neural networks background. Like, so like for me, like the reason why I started thinking about this problem is because I was thinking about some parallels between optimizers and memory-augmented neural networks. Okay, so like here's a very quick one-slide introduction to memory-augmented neural networks. Like so, in the family of, like in the space of neural networks, right? So we have the simplest class of neural networks, like feed-forward networks, like where like you feed in some X, you get some Y out, right? Like so, it's an MLP, no memory, right? Like so, stateless in that sense, right? Then we have memory augmented architectures like recurrent neural networks and LSTMs. In the case of recurrent neural networks, HT is the memory, right? In architectures like LSTMs and GRU, like so you have a separate cell state. So you have HT and CT, which access the memory and integrate information over time, so that you can make a prediction that is conditioned on the entire history, right? Now, in this space, like, so we also have methods like neural Turing mission, like, which is much more expressive and much more sophisticated in terms of how you represent things than RNNs and LSTMs. In RNNs and LSTMs, like your memory is often a single vector or two vector, but in neural Turing mission, like so you're going to have a structured memory, right? The simplest neural Turing mission is where you have a matrix, like each row is a memory, like you could have 10 rows, which means that you have 10 memory vectors, and more interesting thing here is like, so the network also learns what to put in these memory and how to use this information when making prediction, right? Like, so in some sense, it self-organizes this memory and puts only things that are relevant for the prediction problem, right? Now, if you try to draw parallels between these architectures and optimizers, right? Like, so we have SGD, which is like feed-forward network, right? Like, and we have optimizers like momentum, RMS prop, AdaGrad, Adam, right? Like, which are all like in some sense similar to like simple memory augmented architectures like RNNs and LSTM, right? Like, so what would be an equivalent of neural Turing machine or optimization, like or optimizers, right? So this was like the motivating question for me to start thinking about developing memory augmented optimizers. So I think what I will do today is like I will present the general idea of neural Turing machine style optimizers, okay? But I will also give you 3 examples, each focusing on different problems and how memory can be used to solve these problems more efficiently. Okay, well, like for people who are familiar with methods like SAG, so you might say that memory augmented optimizers already exist, right? Like, because in SAG, like, so you use memory of all the gradients, like in the examples, like for the data set as a proxy for gradient computation, right? So these are mostly variance reduction methods, right? Which focus on reducing the variance, and we have SAG, SAGA, and a bunch of things, but even though they have a lot of nice theoretical properties, like, so they kind of struggle when you want to use them for like very large models, okay? So in that sense, so this is the current spectrum of algorithms we have. So in one end, we have things like SGD, which are really very close to, well, SGD is memoryless, like, but things like momentum, AdaGrad, Adam, they have very little memory, right?
Like random search would be memoryless, right?
Yes. Well, it's not a very useful.
It's useful for hyperparameter.
Yeah, I could put it there. So, and in the other end, like we have things like SAG, SAGA, which are computationally, which are extremely memory intensive, but not very practical, right? Like, so the other way to look at memory augmented optimizers is like, can we design optimizers which are somewhere in between, like, so which uses reasonable amount of memory so that they can be scaled up for deep learning experiments. Okay, so this is like a second motivation for like what I'm going to present today. Okay, so as I said, like we're going to talk about like the idea of memory augmented optimizers. Then I will also show you 3 examples, like so how to use memory for accelerating your optimization process, how to use memory for improving the generalization of your like training, and also how to use memory for reducing forgetting that happens in lifelong learning. Okay, so first let's look at memory for acceleration, which also will introduce the idea of optimizers. So it's kind of unfortunate that the student is not visible because of the. Can you move that a bit? Or
Can you move it?
no, this is not mine. Like, so it's from the. Well, so while we are trying to move the thing, so this work was presented at ICLR a couple of years back. It's for memory augmented optimizers for deep learning, which was primarily done by my previous student Polymeric, who went to do a physics PhD after doing deep learning. I tried convincing him to do deep learning, but he was more interested in physics. Okay, yeah, so you can see here. So what is memory augmented optimizer? So we are going to design optimizers which will have a fixed memory buffer like neural Turing machines. Okay. Now this means we need to answer a few questions, like so what to store in the memory, right? Like so and how to use it. So first let's talk about what to store in the memory. Like so you're going to store like what I call as critical gradients in the memory. Okay, so there are many ways to define which gradient is important for the optimization process. Okay, so the simple definition that we are going to take for now is gradients which has high relative norm or critical. Okay, so we're going to put these in a buffer which is a priority queue, and because the initial gradients are going to have high norm, like that they will never get out of the buffer, we need to flush them out at some point, right? Like so we're going to store the L2 norm of this gradient as a priority and decay this priority over time. Okay, so this means that gradients, when they enter the buffer, at some point they are guaranteed to leave the buffer. So leaving room for other like new gradients to come in. Okay. Now that's about how to store things in the memory. Now, how do we use this memory content for updates? Right? So there are a few options. Well, there are at least a couple of obvious options. Like one thing that you could do is just aggregate through sum or mean, right? Like, so whatever way you want. Like so you could consider these gradients in the buffer along with the current buffer, current gradient that you have. Okay, so you could take an average or you could sum them and then average. So whatever you like, right? Okay, so now if you think about it, this is a bit similar to momentum, right? So what we do in momentum is you have one vector, and this one vector stores the history of all the gradients you have seen in the past. Now, instead of storing all these gradients implicitly in a single vector, I'm picking relevant gradients and storing them in my buffer, and I'm going to use this to accelerate the training. Okay, as I will show you, this is actually much better in terms of accelerating when compared to classical mode. Okay. So however, this does introduce two hyperparameters. So one is topsy, which is like how many buffer entities to store. So then we have decay, like how do you decay? So okay, so I will show you that like these are not very brutal hyperparameters. Like you could set them to a reasonable range and you will be fine. Okay, so for example, you will always pick top 5 gradients or top 10 gradients. So decay, we have a couple of rates I will suggest there, and mostly these kind of hyperparameters. Okay, now how do I use this buffer like while doing optimization? Like so, I would like to see this more like a wrapper for all the existing and even future optimizers. Okay, so here is the slide of SGD family of optimizers, right? Like so what we are going to do is we are going to replace the GT that you see here, like in all these optimizers, with the aggregations from the buffer and the current gradient. Okay, so it's a simple wrapper. You could use it on top of any optimizer, and the hope is this is going to accelerate any optimizer that you use. Like, so if you have Atom, you do Atom C, you should see some speed up. SGDM, add SGDM C, you should see some speed up. Okay, so this is the idea. Well, the paper does have some theory to show that under strong assumptions it converges, but I just wanted to show you some experiments like before I move to the next idea. Like so we did a bunch of experiments like covering computer vision, NLP, different kinds of architectures like yes, coordinates, LSTMs, transformers, etc. And we tested all the 4 optimizers like here, SGD, SGDM, RMS prop, Atom, and compared them with their critical gradient counterparts. Okay? And for all these experiments, like hyperparameters were properly tuned with same amount of compute budget for tuning for all the optimizers. Okay? So just to make sure that it's a fair comparison, because we have 2 extra hyperparameters. So this is like a summary of results. Okay, so in the left side, you see the acceleration. Okay, so it's a bit dense figure, like, but what you should really look at is like, for example, you see here. So if you do SNLI task with the coordinate and you use RMS prop as your optimizer, now this is the speed up you get between RMS prop and RMS prop C. Okay, and just to give you another example, like so this is a multi-verse data set for dialogue, Roberta, RMS prop, right? Yeah.
Is acceleration and number of steps or like wallflower?
Okay, well that's a good question. So this is the number of gradient updates. Wall clock, we need to optimize our implementation.
Your optimizer state takes a lot more memory now. You have to lower the batch size.
Yes, it's a bit slow. Like with efficient implementation, you could get up to 1.2x the time of the vanilla optimizer. But this is like what we show here is like the number of gradient steps. Okay, so you do see in some cases like there is not a lot of acceleration and even like a slowdown. But one thing I would like to highlight is these are typically the hyperparameter choices you won't pick. Okay, so for example, when you do C for 100, you will not use Atom. You'll be using like SGDM, like which is in the top. Okay, so it doesn't work in some cases, but it so happens that they are not very crucial cases. And in the right, you see the corresponding generalization improvement. So even though when we did this work, we were not optimizing for generalization at all. Like so our goal was acceleration, but this does help in improving the generalization a little bit. So here are some figures, samples from the previous graph. Like so, these are validation complexity. My pointer is not working. So the validation complexity for two different data sets, and in the middle you have validation accuracy. So accuracy higher the better, complexity lower the better. For ordering, so the solid lines are the critical gradient versions, and the dashed lines are the normal optimizers. Like and like you can notice that the solid lines, most of the cases, happens to be better than the dashed lines, and that's true for a bunch of tasks that we tried. So as a summary for the first part, right? So what we introduced is this idea of like having a memory buffer, like which stores critical gradients, and so I would put it somewhere here, right? And it's a general wrapper. You can use this wrapper on top of any existing gradient present optimizers, and as you rightly pointed out, it increases the memory complexity for sure. Because if you store 5 gradients, then you need 5x more memory, right? Like so, but thinking about it from that perspective, like so, this is much cheaper memory, and you can afford to do this for like even a reasonable size vision transformer. Okay, so and there are actually certain tricks to avoid this memory complexity. Like so, you could just quantize things in the buffer, like and dequantize when you want. Like so, you could optimize for it. And we have trained like even bigger models with this optimizer, it works fine. And well, like so the goal here really was to learn to optimize, okay? But of course we are not learning, we have a heuristic for deciding what is a critical gradient and putting it in the buffer. So it's still a heuristic algorithm, like but the goal really here is to learn to optimize. And for some general recommendations, like you can either use the same learning rate, sometimes we find reducing the learning rate helps. 5.0.7 is like a very common hyperparameter configuration that you could use. If not, you could try 20.9. Depending on the type of task, it varies, and normally some works for SGD kind of methods and mean for Adam kind of methods. Okay, so this is memory for acceleration, right? Like so, but I want to highlight, yeah.
So, in an infinite RAM, infinite GPU model, this makes sense. But what do you say to people who say that rather than spending extra memory on my optimizer, if I had extra memory, I'd rather make my model bigger? Which is a challenge we definitely come across with talking to industry.
Well, interestingly, nobody has asked me this question before. You could do that, but even for larger models, right? Like so, this idea of augmenting your optimizer's memory should help. But it is just the question that how much memory you have, like how much you can afford to use.
You're sort of assuming a world where you have extra memory available.
Yes.
In that world, industry people are like, well, I'll just make my model bigger. I don't want to learn about it.
Yeah, but you don't need a bigger model for every task, right? Like so, like one place where I see these kind of optimizers being useful is like tasks which are fine with underparameterized models, right? Like so we don't need GPT for everything. Like unfortunately, that is what a lot of NLP people are doing. Like so we are using these big models for tasks where you could do well with just 10 times smaller models, right? Like so in small model regimes, yes, this is definitely like a boost. But even in large models, like I would like to somehow scale this up. So which is why, like I mentioned, things like quantization and other things. But then, like, so we tried quantizing the optimizer itself. Like, so there are some work which tries to do quantization for optimizer, but quantized optimizers are very brittle. Like, so like they crash all the time, like, and it's not clear like how to make them more reliable.
So this stuff is also used in RL, where they call it like a replay buffer.
Yes, it's kind of similar to the replay buffer in all too. Just make sure I am following the time. Okay, so now I want to talk about so this idea of augmenting a memory and using it for a specific goal is general. Okay, so in the previous example, like I was using the memory with the goal being acceleration, right? Like, so now you could also, but we saw some generalization improvements, right? But you could also consider generalization to be your goal. Like, so if I want to generalize, like what kind of things I should be storing in the memory and how do I generalize better, right? Now, so this question, like I think we were starting to investigate mainly because the critical gradient versions that we experimented with worked really well with is GDM RMS prob. But whenever we tried Atom, so we did not see a big boost in using critical gradients. Okay, so like the boost was little, sometimes very minor, sometimes matching the performance of Atom, but we did not get the same like improvements that we got with RMS prob or SGD. Okay, so we're trying to understand why this is happening. Okay, so I'm going to explain why this is happening, which kind of also helped us to come up with better ways to do these things. So this is like work by my current PhD student, like Pranshu. Like, so this is for promoting exploration in memory augmented Atom using critical momenta. So the goal here was really just to make memory augmented Atom work better. Okay, so and the way in which we are going to do that is by encouraging a little bit of exploration so that the optimizer generalizes better. Okay, so well, like in general, like so we know that adaptive optimizers are faster in conversions, but they suffer from poor generalization, right? Like, so Atom typically is known to converge to the nearest minimum very quickly, which kind of works if you're in nice regimes like settings where this is not an issue. Like, but in settings where like you have a lot of bad minimas, like Atom, depending on where it starts, it's going to quickly converge to these bad minimas, right? Like, so now, which we thought would be the reason why Atom C was not doing better, which means we need to do something more than the critical gradients in the buffer to avoid this behavior of converging to the nearest sharp minimum or poor minimum, right? So how do we do that? So this this kind of goes back to why CG was not working for Atom. Okay, so here is a nicer illustration of how critical gradients was working, right? Like, so in a naive Atom, like, so you would just consider the current gradients, right? Like, but in Atom C, you used the critical gradients from the past, right? Now, it so happens that when you use these bunch of gradients from the past, most often things work fine, but sometimes, depending on where you are in the raster phase, you could have these gradients cancel each other. Okay, so which means you make no progress and you just converge to like whatever is closest. Okay, now here is an example. Okay, so this is like a standard tie loss function. I forget the name. So your minima is here. Okay. You start here. So this is the performance of Atom CG or Atom C. By the way, I don't put Atom here, but Atom doesn't make progress at all here. Okay, so this is Atom C. It starts making some progress, but at some point, so you also see the buffer quantities and their directions here. Okay, so the quantities kind of cancel each other. That the optimizer gets stuck there and makes no improvement. Okay, so we kind of suspect that these gradient cancellations occur primarily near sharp basins. Okay, so like because you have large norm around this region, like there's a directional gradients, and when you put all these things together, gradients cancel each other. Okay, now how do we avoid this issue, right? Like, so like I want my optimizer to somehow explore this place and reach the minimum, right? Yeah.
you just redefine like your priority score as alignment with the current buffer then rather than a large norm? Like you just take a inner product and if they're orthogonal, you don't add it or something like that.
Can you repeat your idea?
So the buffer, your priority metric is L2 norm. That's not taking into account the direction of the gradient.
Yes.
If you're worried about cancellation, say when you get a new gradient, inner product it with your current gradients, and if they're very not aligned, then you don't add it to your buffer or something like that.
You could do that, but then that means you will never change directions.
Yeah, I mean this would be within some tolerance sort of thing.
Yeah, well, I think okay. So the way I'm going to explain the new, I think maybe it's implicitly doing what you are saying. Like we can talk about it like once I explain the idea. Okay, so what we kind of modified here is like instead of using critical gradients in the buffer, like so now we are going to store critical momentums in the buffer. Okay, now what is a critical momentum? Like so, these are just the momentum values during the time I picked these critical gradients. Okay, so instead of storing the gradients, I'm storing the momentum. Okay, so now this is how it looks like pictorially, right? Like so, at different points, I select momentums, I put them in the buffer. Okay, now they do capture the gradient information, but the nice thing here is most often momentums align with each other because it's going in a direction, right? So, so you will not have the cancellation much, but you will see them shifting in directions. Like so the shifting is, I think, still allowed, but it's a bit difficult, but it's still right. Now, how does this critical momentum work? So here you see the same figure like with Adam CG and Adam CM. Okay, so Adam CM, because it has these aligned vectors in the buffer, right? Like so, as you can see, the directions don't cancel much, so it makes the push that is needed to get out of the region, and it reaches the minimum. Like, yeah.
Does it overshoot after if the?
Yes, okay, that's a good question. This optimizer is not guaranteed to converge. Okay, so it will overshoot, but we do want it to overshoot because let's say it gets stuck somewhere here. Like unlike Adam, this optimizer will overshoot and get out of the region. Okay, now depending upon how you tune your like how you set up your hyperparameters, you could actually control when they overshoot. So you can set the hyperparameters, like the two hyperparameters that we have, in such a way. Well, I'm going to show you some experiments, like a couple of slides. Like, so you can set them in such a way that they will escape sharper minimas up to a certain level of sharpness. When the region is very flat, then they are just around the region. Of course, they're not going to converge, but they won't like get out either. In those cases, you could switch to normal Adam, and you're going to quickly converge to the minimum, or you could just reduce the learning rate. Yeah.
Do you have any idea what that sharpness is? Like what kind of relative to that? Okay.
No, well, that's the kind of things we are trying to figure out. So well, one of the motivations for me to give a talk here today is like we are a bunch of deep learning researchers trying to do optimization theory. Okay, so I'm very much open for feedback on like what kind of things that we could explore to understand these things better, right? Like so, like I used to develop architectures. Like so now I'm using the same skills in developing optimizers. So it works, but we don't know why it works. So okay, so yeah, so this is the figure I was talking about. Like so here, like we have this toy setup, like where like we have two minimas, one sharper, one wider, and Adam, as you can see, like gets stuck a lot in the like in the sharper but suboptimal minimum, I guess. Like Adam CG2, but Adam plus CM doesn't get stuck often. Okay, so and if I change the hyperparameters like to be more explorative, then I could even remove that one particular red score too. Okay, so in some sense, like this is an exploratory optimizer. Like, but how to control the exploration is something that we are actively figuring out and see if we can make use of this to train larger models. And we also, well, this is the sharpness as well. Like, so basically, we show that like AdamCM can escape the sharper regions like much better than like other variants. Like, so we also compare with SAM. I'm going to show some results like where we show that AdamCM can do better than SAM. Even though SAM is explicitly designed to like have like a flatter solution, like reduce the sharpness, AdamCM finds even flatter solutions than SAM. Okay, so yeah, so here are some deep learning benchmarks. Like, so here we do CFARS and ImageNet, and I think these are corners and mobile, like a bunch of different architectures. Like, I don't have architectures named here. So this paper was just trying to make Adam plus variants work. So we don't have these GDM results here, which is something that reviewers often criticize because these are the tasks where Adam is not the best optimizer. Okay, so nobody uses Adam for CFAR or ImageNet. Okay? But our goal was improving Adam, so we are just comparing Adam variants. And here you can see the performance, like and AdamCM is better, and it is also complementary to SAM, so you can actually combine SAM plus CM. And it does well in online learning settings too. And well, this is kind of analyzing, like this kind of verifies like the design choices. Like, so instead of using gradients, if you store momentum, then you can see the buffer variance is low, and the similarity of different entries in the buffer is high. Yeah.
Do you have any intuition as to why it is better than SAM? That seems a bit. That's interesting.
I think it's because of the exploration. Like, so, like if you think about how SAM works, like, so it's more local, right? Like, so it just looks around the region to find flatter regions. But because of the overshooting properties, like, so this can explore and go even far away from where it started. Okay, so well, quick summary. Like, so like when you store momentums instead of gradients, right? Like, so you can overcome the limitations of adaptive optimizers, like that they get stuck. It provides exploration benefits by searching for flatter regions, and you can also get like better generalization. Okay, so, but this is like something that we are actively working on. Like, so we are trying to figure out why, like how to properly control exploration, so that you can get all the benefits of exploration without like overshooting and like getting out or diverging, right? Like, but we are also trying to figure out if this can be achievable, like if this is achievable with just a single vector like momentum instead of having a memory buffer, because the fact that we need a memory buffer limits the applications to large language models or any other big models, right? Like, so, like, but this is also like, I think I'm also curious if we can achieve these exploration properties with just one vector, like momentum, instead of having multiple vectors. It does that. Like, it does have the exploration phase, but isn't that like a more uninformed exploration? Like, because you have a fixed cosine rate, and it explores exploits.
In the original SGDR paper, I think they talked about making their exploration bigger over time. At least the ideas from discrete optimization that they're trying to be doing. That's what you do. Is if you get back to like the same local optima, you make your exploration bigger the next time.
Yeah, well, yeah, I should check the cosine literature. Okay, I think I have 10 minutes. Like, I'm going to quickly go through the last part, which is like how to use memory for reducing forgetting. Okay, so this is also work by Crunchroll. Like, so this is task-based accumulated gradients for lifelong learning, which was presented at COLA's a couple of years back. Like a very quick introduction to lifelong learning, like in case you have not seen lifelong learning before, right? Like, so the idea here is really to design systems that can learn continuously over lifetime. So there are many names for the same problem, like continual learning, never-ending learning, etc. And there are many variations, right? Like, so you could consider pure online learning setting, like where it's the same task, but distribution sits over time, like, or you could also have these nicer configurations that people call as task incremental learning, like where you learn the first task, then you learn the second task, then you learn the third task, etc. And like you expect the agent or the network to be better in all these tasks. Okay, so we're going to consider task incremental learning for this particular project. There are many advantages of doing lifelong learning, like so, like the hope is we are going to get sample efficient algorithms, like they become sample efficient in learning the future tasks through forward transfer and backward transfer. And I think this is the way for general intelligence. Like, so if you care about general purpose agents, then they should be able to pick up any task, and also at a rate which is like much quicker, right? And this is necessary if you consider learning after deployment, which even ChatGPT-like systems don't do, right? So this is why we should be doing lifelong learning, but it is not an easy problem. So there are a couple of major challenges. Like, so one is plasticity. I'm not going to talk about it today. The other challenge is this idea of catastrophic forgetting. Okay, so what is catastrophic forgetting? So let's say I learned the first task, and this is my ideal configuration for the first task, and this is actually a bunch of configurations which are okay for first task. Okay, so now when I learn the second task, this is a bunch of configurations which are okay for the second task. Okay, now if you see, there is some intersection where if your network is in this particular configuration, then it is good for both the first task and the second task, right? So the idea here is really to find that intersection, and as you can imagine, this intersection becomes much smaller when you have many tasks, right? So at some point you do need to forget something. But when you do naive stochastic gradient descent, there's a very high chance that your configuration shifts to somewhere here, becomes better in the second task at the cost of forgetting the first task. Okay, so this is what we call as catastrophic forgetting, right? Like, so you could have much worse algorithm which can never balance anything, but ideally we are looking for this really nice kind of optimizer which figures out the common point in between the two. Okay. Now there are many solutions for catastrophic forgetting. At some point, the field was just thinking about catastrophic forgetting, like for 5 years or so. This is an outdated slide. But the point is, there are different ways in which people try to solve catastrophic forgetting. We often propose new algorithms and architectures for solving this problem. Okay. Now we're going to look at this from the optimization perspective. Okay. Simply because even though we propose new architectures, algorithms, we always use SGD and Atom for optimization here. Okay. Now, if you have read lifelong learning papers, you would often notice that people don't use Atom in lifelong learning. So in lifelong learning, SGD is the most popular optimizer for both forgetting and plasticity. Atom is terrible, so people just use SGD, right? Now, this doesn't make sense because we had so much progress in adaptive gradient methods, right? Like, so we are kind of throwing away all this progress and go back to SGD for lifelong learning. So which brings us to the question of, can we design adaptive optimizers for lifelong learning, right? Now, to figure that out, we need to understand why SGD forgets less when compared to methods like Arnold's problem Atom. And one theory is adaptive gradient methods are very aggressive. Okay, so what do I mean by that? Like, so SGD, when compared to SGD, when you do RMS prop, it's going to quickly change the learning rate according to the gradient statistics, and it is meant to solve the current task faster, right? So when you solve the current task faster, there's a high chance that you don't consider where you came from and do justice to the previous task, right? So now this means we should be able to design adaptive gradient methods, but the gradient adaptation happens based on the objectives of lifelong learning, which is what we are going to do. So what we are going to do is we are going to do task-based gradient accumulation, okay? And we are going to regulate the model updates in such a way that when you see two uncorrelated tasks, right, like MNIST and some other image classification tasks, you want to prevent forgetting, which means you want to take smaller step sizes, okay? And when you see two correlated tasks where you can have knowledge transfer, then you can be aggressive and learn faster. Okay, so basically being very careful in your steps, depending on the current task agrees with the previous tasks or not, right? Now, this idea is similar to critical gradients in the sense like this is also a wrapper. So I'm going to explain it through RMS prop, but you can do this with Adam or any other optimizer. So here is the normal RMS prop update equation, but with a little bit of changes, right? So instead of just having the root mean square of the gradients, right, which is the VT vector, I have weighted VT vectors, like where the VTs are task specific, but each task I'm going to store VTs and I'm going to weight them here. So how I weight them, it's based on these alpha values. Like I want to finish on time, so I'm going to skip explaining how it exactly works, okay? But the idea here is intuitively, like what is there in these equations is like whenever the current gradient agrees with most of the tasks, I'm going to increase the step size. Whenever it disagrees with a lot of tasks, I'm going to be conservative and use a smaller step size. Okay, so that's the idea. And this simple change actually makes adaptive gradient methods work for lifelong learning. Okay, now just to show you one example, so let's take the 5 data set, right? So in 5 data set, you see SGD is the best optimizer. Like Adam is here, I guess, yeah. So Adam is here. So this is forgetting. So like it has to be smaller, right? So as you can see, Adam is forgetting more than SGD. But when you do tag Adam, like it has significant reduction in forgetting. Like it works much better than SGD. Okay.
What would an ideal or get here? Like, are these still really high numbers?
It depends on how you define an ideal algorithm. Like if multitask learning is your ideal algorithm, that will get very high score. So usually multitask learning is an upper bound for this kind of continual learning setups. Okay, have 2 minutes. So
yeah, just a reminder, we have to start wrapping things up in a few minutes.
yeah. So 2 minutes, I'm finishing. Okay, so,
No.
okay, I'm going to skip
Yeah.
these things. Okay, so one thing I want to say is like this is an optimizer. So you could combine this idea like with any other algorithmic and architectural solutions for lifelong learning, right? So here we combine tagged optimizers with state-of-the-art algorithms like EWC, GEM, experience replay, etc. And as you can see, this just gives you free boost. So you can take any lifelong learning algorithm of your choice, switch the optimizer from RMS prop to tag RMS prop. You're going to have even better reduction in catastrophic forgetting. Okay, so here we show that this actually helps in multitask learning and other scenarios as well. But in summary, like so we have this tag, which is a general wrapper on existing optimizers, and this was the first work to actually show that you can do adaptive gradient methods for lifelong learning and still do better than SGD. Okay, so I think I will stop here. Like so I gave you some examples for what I mean by memory-augmented optimizer. Like, and I would be happy to chat with you if you have questions, suggestions, or if you think some of this can be useful for you. So I will stop here. Thank you.